Okay, so it's recording. Again, for recording's sake, I'm taking your permission from all of you to record this. Program is getting recorded. Everyone, welcome again. I will share my screen.
These are doing all jogging, so I'm not sure.
Just a couple of checks. Blake, could you see the screen?
Yes.
Okay, let me. Let them start. Okay, so everyone, the session will be, we have a lot of slides. I'll be talking some theory, and also we'll do some hands-on, and also we'll focus on some concepts. And also I'll be giving some references to some notebooks related to deep learning. So Blake and everyone, I want to understand from the team who has exposure to machine learning, deep learning, big data, just how are the overall background. We can't go through individuals, but Blake, someone can comment.
Yeah, kind of like a show of hands. Anyone doing machine learning, deep learning? Awesome. About half of us. On the HPC, obviously we run quite a lot of machine learning and deep learning neural networks. In fact, I'm answering an email right now from the BI's group asking questions about deep learning neural network training.
Wonderful.
So it's a good time.
Who has any exposure to Apache Spark? Okay, wonderful. Pandas, of course, everyone. Pandas, everyone use, right? There was some TensorFlow and Keras. Oh, wonderful. Scikit, definitely a lot of people will be using. Okay, wonderful. That would help. Okay, thanks again. Let me, sorry. Where I am. Give me a second. I'm trying to figure out the share. Okay, I did pause the share. Now share is good. I'm starting my slides here. Okay, thanks again, everyone. Let's keep it going. So it may be around 2.5 hours or 3, depending upon what we want. In between, there will be a break. And my colleague, Harun, also will be sharing some stuff with you. So the discussion will be focused on large-scale machine learning. The word says large scale. That shows we'll be dealing with the huge data in the industry. So enterprise AI with Apache Spark and open source Delta Lake. Apache Spark and Delta Lake are open source products. Apache Spark is quite famous. I've been in the industry for 5 to 6 years interacting with the community. I don't work with these people, but I watch just like you. I have mixed feelings for this season, but I am fortunate to work with some people like Reynolds. Anyone of you know some of these people? Matai is the creator of the Apache Spark. He's also co-founder of Databricks and Reynolds. These two are some of the people who created Apache Spark, and they're chief technology officers and chief architects of Databricks, for which I work. So I also interact with kids. I teach some coding classes in the weekends whenever I get time. Many times I think I teach them, but I realized I learned a lot from these kids. So the topic is large-scale machine learning, enterprise AI with Apache Spark, open source Delta Lake. So Delta Lake is a wonderful open source product recently released by Databricks, which is also being used by more than 500 big companies. We'll also talk about this during our discussion. So most of the discussion, Blake, keep it for a discussion in between. Some people want to ask questions. Please interrupt me. We'll take it forward. More like a dialogue, not a monologue. So a lot of companies use these technologies, Apache Spark. Nowadays, a lot of data analytics software to do not only general data analytics, advanced data analytics like machine learning and deep learning. So as the data grow, a lot of problems comes into the picture. So these companies are working hard to gain control over these technologies for a better customer service, better sales growth for their survival and to adjust to the competition. So why these companies wants to use these technologies? So essentially, any organization, any universities, any enterprises, profitable or non-profitable, they can only survive through their customers. So I don't know if you heard from Peter Drucker. He says the purpose of the business is only has two basic functions: marketing and innovation. To create a customer, because through customers, they get income through which they survive. And in the process, they offer services, products, but to serve the customer. So in the process, they make money. But in the same, Peter Drucker says the aim of marketing is to know and understand the customer so well, so that the product or service fits him or her and sells itself. So nowadays, people don't like selling. It should be seamless, frictionless selling. So that's where, please understand the customer so well. Understanding the customer so well means all these companies trying to collect customer data, trying to understand their preferences, trying to understand how to reach these customers effectively and create a great experience for these customers. That is the goal of a lot of companies. So it has been goal of the companies for a long time. So they collect a lot of data. Pawan and Shiva, you guys are doing this data warehousing, right? So you collect a lot of data here and you put into Oracle data warehousing systems and do your reporting. It's all good when the data is not too big. But past for 5 to 10 years, you might have seen data has exploded. People start connecting to the internet, to their cell phone. A cell phone is a kind of Internet of Things. People talk about Internet of Things, but cell phone is the first and foremost Internet of Things. And even nowadays, the connected cars, autonomous cars is a norm. So this is I like this slide from Nero, last seminar in the US Science. So in 1 minute, what all happening in the internet? So many blogs, 2 million minutes of Skype calls. You can choose any of it. So customers are interacting in the web through companies or social media forums and sharing their ideas. So it is an opportunity for the companies to know about these customers. So in the process, the companies want to collect the data and want to create a great experience for the customers through a product personalizations, product recommendations. So that they want to win the customers, they want to outweigh the competition, and they want to survive. So how they are going to do that? So they not only collect the data to do a personalizations. Companies are using advanced data analytics like machine learning, deep learning, natural language processing to read and understand what customers are using on the social media forums. So the companies want to collect the data and convert into information and convert into knowledge and wisdom. People say it's not wisdom, but actionable insights so that they can customers. So as the data is exploding, the enterprises are going to a big data technologies. So Apache Spark is the leading software, open source software, created by folks from Databricks, university PhD students in UC Berkeley, Matai and Reynolds. 6, 7 years, 10 years back, they were students at UC Berkeley, just like you, research folks. And the software is an open source used by a lot of companies. So Apache Spark is a distributed computing software. So distributed computing software means you have a lot of data, either in Hadoop or Azure, Amazon. This data, the Apache Spark computes in a parallelly through multiple machines. They process in parallel. When you do things in parallel, you can do it fast. So also it's a manageable. The systems can able to run. A lot of other proprietary systems like Oracle, SAP, and all these systems, they cannot scale because the data is exploding. Apache Spark also does real-time data analytics through streaming. The events can flow through the system. Apache Spark can able to handle through streaming and can able to write into multiple sources. So it can read from a lot of sources, it can write into a lot of sources, either in a batch way or in a real-time streaming way. So Apache Spark also supports, interestingly, this is a very beautiful software. People really like it. Interestingly, it supports Python. I think all of you like and love to code, and also Scala, which is a functional programming. It also supports Java and R. It can do machine learning, it can do streaming, it can do batch processing, SQL, even it has a graph computation. That's why industry loves it, even including companies like Apple. Some of the teams use this software, and almost every company uses this software. So if you see, it's very beautiful. You just read it, read a data. It will be converted to a data frame, just like your pandas data frame. And you can able to write, df.write. When you write, you can specify the formats, like CSV files or Parquet is one of the open source file format created by LinkedIn folks working with Cloudera. And you can create, save as a table. You can create as a temporary table or persistent table on the cloud or on the cluster. You even see this simple syntax in pandas. pd.reads_CSV. It's a Spark read.csv. It goes very close because industry wants people resources with a less learning curve. So people with Python and pandas background, they are very quickly adapt to Apache Spark software. Interestingly, recently there is some more developments to make it more easy. If you see a typical pandas, you have a pd.read CSV, then you can take these columns, then you can display some of the rows. This is a typical pandas, one of the file. It took 1.39 minutes to execute on a cluster because it's a simple pandas. So you cannot distribute it on the cluster. Even though you're running it, it uses a single machine. Of course, there are some methods to scale them for multiple machines. There is a open source software recently came. It's called Koalas, a pandas API on Spark. So what Koalas does is, see here, if here you're importing pandas as a PD and reading it, Instead of pandas, you'll import as a import Koalas. So it's exactly does like pandas. A Koalas.read, same syntax, no difference in the syntax. Same data, same display. But when you are using Koalas, your pandas became distributed. The Spark distributes on multiple computers. And see if you see, I don't know if you can see this. Blake, can you see this? It took 8 seconds.
Yeah. I can't, but yeah, it's big enough. Kinda.
I can tell it's a data frame.
All right. That's
Correct.
free to move forward. I will move out.
Correct. Correct. So the industries want to utilize these resources so that learning curves are less, because you have a lot of problems to solve, not just syntax problems, not just basic roadblocks to do basic data analysis. So any skills of Python and Panda skills are very hot and can be easily adapted to the Apache Spark enterprise world. So Apache Spark also is aligned to machine learning and deep learning. So Apache Spark has their own machine learning libraries, but as far as deep learning, it aligns with TensorFlow, Keras, and PyTorch. So under the hood, so Apache Spark will run on top of them. So Apache Spark is another abstraction, just like a Keras. But since Apache Spark can deal with a lot of enterprise data in a distributed fashion, so it can build data pipelines and interact with TensorFlow and Keras and PyTorch. And recently, there is one more development. There is a software called Horoward. I'll talk about that, which you can use it for a distributed deep learning. Deep learning, when you're running on GPUs, it runs faster, you know. But still, if the data is too huge, like Uber and few other companies, so Uber came up with an open source software called Horoward, so with which you can able to distribute the deep learning on multiple GPUs. Okay, so Spark supports that also. So with all these concepts, people love this software and people start doing the big data. Just does that mean they have a smooth road? Not really. Everyone want to, this is the aspiration. Industries want to conduct data science and machine learning on all the data that is using Apache Spark, because a lot of customer data, a lot of video data, a lot of click streams, the huge terabytes of data, when they collect into Hadoop or clouds like AWS S3, Azure data lake services, when they collect it, they want to use Apache Spark and do advanced machine learning. But to do a machine learning, the data needs to be clean. If your data has issues, whatever the junk in, junk out, data in, data out, if it is not good. So a lot of companies do two types of data processing, big data processing. So many companies want a real-time data. They use softwares like Kafka or Kinesis, some PubSub softwares. So Apache Spark helps you to do the Spark streaming, where you can have a streaming analytics. But companies also want historical data. When you're doing a machine learning here or a reporting, you want a latest data, you want a historical data as well. So that's where not only streaming data, they need to store data into data lakes. That's what they do. They want a historical data, so they use data lakes. So they call it as a Lambda architecture, if you heard that, Lambda architecture. So apart from that, as the data is flowing here and as the data is coming here, and you need data for machine learning, it has to go into multiple hops because the data will be coming every day. Data will be, you need to use historical data. Data will be flowing every day. And there could be merges, there could be updates. you will have to do a lot of cleanup. So messy data, fixing the mistakes is a common task a lot of people do, because these data goes into files like JSON files, Parquet files, CSV files. So there are no restrictions for this data to get into these big data stores. So that's why they use validation techniques, reprocessing techniques, all the steps people do. And even updates. As I mentioned, you need to update your customer data, type 1 merges, type 2 merges. In data warehousing world, there are the terminologies like type 1 merges, type 2 merges. If a row exists, update the row. If the row doesn't exist, insert the row. It's like upsert. If in type 2 merges, if a row exists, you insert a row, inactivate the historical row, and update the rows. So all those updates, merges needed. So doing merges on a huge file systems, because you are doing merges on the files. As I mentioned, big data is all about files, CSV files, JSON files, Parquet files. All these updating these files and folders is a nightmare. So, and also if someone is scheduled to doing a reporting, so at that time you should update. So you need to schedule. So it is not easy. A lot of people are doing it, but it is not easy. Some people say, yes, we will do it. Yes. Blake, do you like this?
Yeah, I feel that way a lot.
Yeah, they'll say, hey, man, hey, we do it. Though it's difficult, we do it. So, but not everyone can do this feats, right? So that is where industries are struggling. But definitely they are better than last year, better than 2 years back. But still, there are challenges. So that's where companies are looking for even a better software which can enforce schemas, which can enforce some ACID transactions, that type of things. So that's where a beautiful software recently released in the market, open sourced by Databricks, the creators of Apache Spark. It's called Delta Lake. It's called Delta. It is called Delta. This Delta software has already been used by more than 500 companies. They tested, and enterprises loves that. But Databricks success is not won, but it is because of community. They always try to give to community. So it is announced, and a lot of companies like McAfee, Informatica, Condé Nast, even Apple, a lot of companies use this software. But interestingly, Databricks open sourced it, so any companies can use it freely. They can build their own clusters, or they can use clouds like AWS or Azure, build their own softwares using this, or they can use a cloud software built by Databricks. I'll talk about it. So we're going to have some more discussion on this. Then we will have we'll do some machine learning hands-on exercise. Just bear with me. Any questions at this time? Blake?
We're still waiting for the, we're still waiting for the actual applications things.
Okay, awesome. Are we going at a good pace? Am I going too fast? Blake, is the pace is good?
Yes.
Okay, awesome. Thank you, guys. So the Delta Lake is a fully ACID transactions. So you can have the schemas are enforced on the software. So you can inject the data. You can do some filtrations and cleaning and augmentation. The data doesn't move forward if without certain restrictions and rules. And you can do a lot of next level aggregations. That's what people say, a bronze layer, silver layer, gold layer. You bring the data here into data sets. and do some pipelines and do a lot of aggregations, etc. So you can do updates, deletes, and merges. You can do updates and deletes and merges without having to do so many feats like people do in other without these softwares. So a typical example, typical architecture looks like this. The ingestion tables, people can inject the data into tables. So as they inject, these tables have a structure. Of course, this works only for structured data. Non-structured data still they can store in the blobs, Amazon S3, ADLS, and Hadoop. Even the structured data under the hood, it will be blob storage only, but they will be mapped to the tables. But if we are talking about enterprise AI companies, so customer data, a lot of customer data. So all those are mostly structured data. So the data can be ingested into tables. Then they can refine the data using Apache Spark to refine tables. If people want to do multiple aggregations, so they go to a next layer. It's called Gold layer. So all these things can be done using Delta Lake. So as far as coding, it's simple. If you want to just write into a Parquet format, as I mentioned you, it's a data frame.write. What is a format? It's a CSV format or JSON format or Parquet format. You're using save. Now instead of Parquet, you will say data frame.write.format Delta. So Delta stores the data in a Parquet format. Parquet is a columnar. It saves into the disk blob storage, but maps to the Delta table so that the table will be available to you. You can do the merges, you can run the queries. So basically Delta supports ACID transactions, scalable metadata handling, time travel. If you want to go back last year, this time, I want to see the data. And it's open format, it supports Parquet. And it's a unified batch and streaming. Even the streaming data can come and update the batch data. Suppose you have a huge billions of rows of the batch table, and you are trying to get the new data in the streaming. Your streaming data can update the table. It can do type 1 merges, type 2 merges. So if it can do upserts. It's like a columnar Cassandra, even like Oracle, it can able to do the merges. Schema enforcement, it does enforce schema. Schema evaluation, in the future, you want to extend the schema, you can extend like a NoSQL databases without much difficulty. And it's 100% compatible with Apache Spark. So the computation engine is very powerful. It is fully supported by Apache Spark. Apache Spark is a distributed, so your table can have billions of rows. Your Spark software, since it is a parallel cluster computing software, the data from the Delta tables can be accessed in a distributed fashion. Okay, so the companies with this Spark and Delta, companies can have a neat data, so which is essential for machine learning. So in the big data world, the machine learning has to be done in a distributed fashion. Your general scikit, general machine learning softwares cannot scale. So that's where the enterprises go for Apache Spark. So the Apache Spark has a machine learning libraries. It supports all the algorithms. So we'll be doing some of these exercises today. Blake, do you think you can see a team can have accounts here? community.cloud.databricks.com. Otherwise, they can take 5 minutes as I speak. They can create their account so that they can able to do some hands-on exercise.
Okay, yeah, hold up one second. Let's go ahead and get registered if you'd like to.
Yeah. So if I'll hold this screen for a few minutes.
Yeah, give us 4 or 5 minutes.
Yeah, and also use this sample notebook after you register it. Simple. It's a free. You can use your university account. Just to create, you'll get a activation immediately. So then you can use this link. It's a notebook and another browser window, so that you can import that.
Is there a whiteboard here?
No, I ended up having to use the
They have a
giant
whiteboard marker for. Awesome.
Okay.
Yeah, I'm gonna write down the URL so we have that too. Give me 1 second.
Community.cloud.databricks.com.
Tiny URL.
Yeah. Meanwhile, any questions? Let me just.
I've got a question for you.
Yeah.
So we have Spark on the HPC now, but
Mm-hmm.
we don't have a Hadoop file system set up. Quite yet. How important is that for all of these things you're talking about today? And should that be something I do like tomorrow?
What's that? Could you please repeat, Blake? Let me see. Let me see you on video once. So give me a second.
Oh my God.
Okay. Let me.
Promo sign up and confirmation email, right?
Sorry.
Some validation code.
I didn't get a code, but there was a link to confirm.
That's all I got. I just want to make sure I didn't miss that.
Yeah, Blake. Sorry, I'm sorry. Could you please repeat the question?
Yeah, we have Spark set up on the HPC, but we don't have a file system yet. And I don't understand like how that interacts. You were mentioning that earlier, how that interacts with Spark and perhaps even Delta Lake. You could cover that one more time.
Yeah, I think you can start using it as a. You said you have Spark now. If your teams can't access immediately, at least you can start from the Databricks Cloud, which is a free. So they get to process small data sets. So after that, once you're able to provision for the teams, they can be able to run and deploy the code on the cluster. They can run able to do in a distributed fashion.
Okay. So we should definitely set up a Hadoop file system, right?
What is that?
We should set up, on the HPC, we should set up a Hadoop file system.
Yes. The Hadoop or if HPC has S3 buckets, so your data can be in the S3. So only thing is you will be accessing data in S3, whereas you will be processing using Spark.
Is everyone doing okay getting signed in? Yeah? Okay.
The sign up button doesn't work.
The sign up what?
The sign up button on community.cloud.databricks.
You have ad block or uBlock?
Yeah, I did disable mine for that.
Alright, give us a few more minutes.
Go vulnerable.
Just for a couple of
Bear my
seconds. Critical.
soft baby like computer skin to the harsh environment of the Databricks.
Let's see. Anyone else on the phone? Pawan, Shiva, Dipanshu. Any? Do you have any questions at this time?
No.
Okay. If not, you can sign up for this community cloud. Can I move to Blake? Can I move to next slide?
I think we have 2 more people still signing up.
Okay, but do you need this? This is already noted, right? This URL?
Yeah, I wrote down the URL too.
So no problem. I'm copying this so that in case I can put that on any slide, the sample notebook. As the sign up, let me quickly move here. Sorry. already done this. I appreciate you guys for rapt attention. We covered a lot of slides. So good. We don't want to do this feat. Thanks to Delta. And getting into the machine learning. You all know, you don't need primer on that. Machine learning, the enterprises are solving a lot of problems using the machine learning. So in the machine learning, you know, different categories of problems are there. If you want to know customers' lifetime worth value, so it is a predicting, it's a prediction. So you're predicting the value. So it is a kind of a regression. It's a y is equal to mx plus b. So basically you're finding the slope of a straight line. It's a kind of linear regression, right? And if a company wants to group their customers, so based on some clusters, based on their purchases, based on whatever, and they don't have to give a specific criteria. So a clustering algorithms can group the customers. If they want 10 different groups or 100 different groups, they can able to do. So clustering algorithms. You know, if you come to the classification problems, you know, I'm not talking about image classifications. I'm just talking about basic machine learning algorithms. Image classification and all comes under deep learning, which uses artificial neural networks. That I'll discuss after some time. So I'm talking about basic classification of customer data or general, what you called, whatever you call some signals or IoT signals, or identifying fraud or not fraud, approved or not approved, credit card approved or not approved. So all these decisions, classifications are basically a segmentation with a straight line, a kind of. Of course, you have a polynomial classification also, where you have a polynomial curve which can able to classify. But if you see a basic classification algorithms, mostly linear they use. So your customer churn, if you want to know, when the customers are going to ditch your company, or when a unpaid customer are going to become a paid customer. So you want to know the point where you can able to send a lot of promotions to the customers. So it's a basic classification problems. It's a yes or no decisions. So classification algorithms are being used. Also, enterprises wants to reach the customers with a lot of recommendations. Either Amazon recommendations or Netflix recommendations, Comcast recommendations, or even in your mail, sending some promotions, sending some recommendations through emails, etc., increases the personalizations. You know, all these algorithms uses some basic statistics, but at the same time, these algorithms, regression, clustering, and classification, recommendation algorithms, these algorithms are coded into softwares like Scikit and Spark MLLIB. Scikit is not a distributed software, whereas, of course, it can be distributed using some other techniques, but not easy. Whereas the Spark is industry-wide used already in the big data area, and Spark machine learning libraries are quite famous. People are using. So today we are going to do some exercise with the concepts we have discussed, like reading data as a data frame, and doing some data cleanup, running some models, etc. But these are the techniques people use. So as I mentioned, Spark ML, Spark machine learning libraries, it uses Spark basically, but the machine learning algorithms are coded in these machine learning libraries. So you signed up for it. We have a sample notebook. So we'll do some steps. So basically, you know, in any machine learning task, you know, even in the deep learning task, you know, you get the data, and you need to clean and prepare and manipulate the data. So these are the standard steps people follow. Correct me if you think different. So the people collect the data, and clean and prepare and manipulate the data. Why they need to do clean and prepare? Most of the preparation will be based on if you are using clustering, you have to prepare in one way. If you're using classification, you need to make sure your labels and features exist. So you need to make sure you need to prepare. Sometimes you have a categorical data. You need to convert into indexes and encoding, because categorical is a text. So all these steps you need to do: get data and clean and prepare the data. Then you do the you train the model using the training data. You test the data using the test data. Then when you train it, you get a model, and you apply that model on the test data. Then you know how accurate your model is. Then finally, you want to improve the model with the given data. Hyperparameter tuning, etc. So Spark uses all these techniques. We'll follow these steps today. So once you sign up, I have a sample notebook. I want you to import into your Databricks environment. I'll show you. Give me a second. So if you, okay, because we're not going here. If you don't have this, can you use this tiny URL? HTTPS tinyurl.com. YXN, let me make it a little bit big. Everyone, Blake, can you please make sure everyone can able to access this URL?
We're all right? Yeah, I'm set up for a quick break. I think everyone's got it, Srini.
Everyone got it? Okay.
A few minutes.
Okay, awesome, guys. So please bear with us. Let's spend 15-20 minutes, then we can take the break. I know it's a long session. Okay. So everyone has this URL. So I'm going to go to my system. Let me share it, new share. Let me share my desktop. So I'll talk a little bit briefly before I hand over to my ex-colleague who can walk us through some steps on the data prep. Give me a second. Okay. So everyone, I believe everyone has this. Let me put this. Hold on. Okay. Everyone can, so that everyone can able to see this particular, let me go to that URL so that I will just show you how to import this. So I can have this. When you use the tiny URL, you will get something like this. Is the correct, Black? Everyone get this? So
yes.
You stay into this. This is the Databricks cloud software, free software for you. So you see here, this is when you click here, this is a workspace. You can create a new notebook, a Python notebook, a Scala notebook, SQL notebook, R notebook. It's just a typical notebook. Then you have different workspaces, different folders, any recent files. You want to store something as a tables, you can able to do here. What are the clusters that are running? To run your code, you need some clusters running. These are jobs. Anyway, let's not worry about this. So go to the core functionality. So when you have this, you can, or when you are in this, you can type something like this, the tiny URL, you will get it. You can import this notebook into your, when I say import, yeah, you can edit and run this notebook importing data accounts. Okay, so to import, you don't have to click this. So what you do is go here. Everyone, please go here. Sorry, let me go to your home. You will have your name here. Sorry, give me a second. So if you say import, it says URL, then use that. Maybe you might have to use the full URL.
Yes,
So
Srini.
just say
Any URL does not work.
yeah, exactly. Just say import. You have this right when you use the tiny URL just for convenience I gave, but this is the URL. You copy this, and click import URL. Just say like this, then you can able to import. You can able to say import. It will come here. So everyone. So this is the data from UC Irvine. We are going to use for classification example. It has data about population data, who earn more than 50K, who earn less than 50K. Then you'll do different steps. You load the data, you see the data, you create a small table, and you do some steps using Spark, Python Spark programming. So you pre-process the data. You need to prepare some steps, prepare the data. You have some steps involved. Okay. So as I mentioned to you, before you run any algorithms, we are going to use some decision trees and random forest. But first two steps are preparing your data. For taking categorical variables, converting indexes and encoding, etc. So my friend, colleague Harun is going to help us on this. Harun, welcome.
Thank you, Srini.
Yeah, let me give it to you, control.
Sure.
Give me, I am stop recording. Stop sharing, not recording, stop sharing. So Harun is here. Harun, give me a second. Harun, I will make you host. Okay. So Harun, walk the team step by step. Then we'll take a break. Then we'll give the time to the team so that they can able to run on their missions. Maybe for 10, 15, 20 minutes, I encourage you to go through the steps where Harun is explaining. Then we'll come back, take a break, and we'll work together where you can able to execute and see the results. Okay, Harun, go ahead.
Thank you, Srini. Good afternoon, guys. Welcome to the session. As Srini has mentioned, my name is Harun. I worked with Srini for last 3-4 years in the big data ML space. So are you guys able to hear me and see my screen?
Yes.
Yeah, great. Yeah, so I started I have 18 years of experience. Started with Java and some ERP software, then moved on to big data. Currently doing big data on Azure and ML. So journey with Srini here for last 3 years in the big data space. We have been exploring, sharing together, sharing multiple sessions like these for various groups over the last 2-3 years. He has invited me to have a session just to walk few steps, walk through with you guys. So it's a great honor to be with you guys, sharing what I know and learn from you guys. Welcome again. So as Srini has mentioned, any ML algorithm has 5 steps. One is to get the data, to prepare the data for the algorithms, then train the data, then test your algorithm, test the algorithm with the data, and then deploy or improve the data. So I'm going to walk you through the first 2 steps, get the data and pre-process, load the data and pre-process, prepare the data for the ML algorithm. If you have any questions, you can ask me anytime through the process. So if you can see my screen here, so Srini will be walking you through the binary classification example. So binary, as you know, is a yes or no, 0 or 1 kind of an algorithm, where you want to learn or you want to predict a certain outcome is yes or no. For example, the email chain, so email spam. So whether an incoming email is a spam or not, right? So if a tumor is a cancer or not, yes or no. So there are so many use cases in the industry or in a daily life where you want to predict certain outcome as a binary, either true or false, yes or no kind of a thing. So that so the current data set what Srini has mentioned from the UCML repository is a census data where they have data for a particular set of people, and their income is whether greater than 50K or less than 50K a year. It's just classification. We are not predicting the actual income of the individual. Rather, we are trying to make a decision, an output based on the features, whether to predict whether the person was earning greater than 50K or less than a 50K. That's the business problem that we will be discussing. So for us to get a prediction, we need the data, right? So we need the data on which we build a model, on which we train our data. We train our model on the data, and then we apply that model on the test data to see how good it is working. So this data set, if you look at, so these are all the features in the sense what are all the available data points or data elements we have. So data elements are basically here two types. One is the categorical and numerical, as the name suggests. So numerical is just the numbers part of it. Categorical is where you have LOVs or list of values or certain categories where the specific set of categories where the data can have. For example, age is a number. When you come to say marital status, you have specific set of statuses, whether you say married, divorced, never married, widowed, etc. Same with relationship, race, sex, education, education number. So education is bachelor's, college, 11th, different grades, and you have that. So education number is again derived based on education. It's a number. That's why it says continuous here, right? So these are all the features available in the data set. So now when we look at the data set, we can actually see what is the data like and what are all the elements we have in the data. So for here, so if you have installed or deployed the Databricks cluster on your machine, we have, if you import this notebook, you can run this notebook on the web. But before that, you have one more step where you need to create a cluster. So if you go here with clusters, you can create a cluster here by giving some just parameters. So by default, it will give you one cluster with 6 GB of data with one machine for processing. And so you can just give a cluster name and then say create, it will create a cluster. So with one driver, 6 GB memory. Once you create this cluster, you can come back here to workspace, and it will you can attach your cluster here, whatever you have your cluster, and then when you run this, it will be automatically running on this attached cluster. So that's one more step you need to do once you import this notebook, once you create your Databricks cluster here.
Okay, well, right there. Have you all created clusters and all that fun stuff? Or do you need some time to do that?
Data, databases, create cluster. Okay.
Yes.
Little spinning wheel next to the cluster main, it's still thinking, or can we attach to it?
Maybe it's a little louder.
So if we create a cluster, well, I have a little spinning wheel next to my cluster name. Now that I've created it, do I have to give it enough time to stop thinking? Oh, it's now solid dot. So I'm guessing good now.
Yeah, just takes less than a minute to create. If you come back to workspace and open your notebook, it will automatically, you should see this attached here, your cluster name. If it is still pending, you can do a drop down and select it to show you the status here. What is the status of the cluster you have created? Or you can go back to your clusters and refresh the page. When it's running, you can come back to your notebook and see whether it is attached to your notebook.
Anyone else need some more time to get the cluster set up?
Alternatively, you could also run the first code and it will assign a cluster automatically.
Oh, okay, cool.
Yeah.
I think we're good otherwise.
Okay. So are we good? Can we continue?
Yes.
Thank you. Right. So this is the file that already is downloaded on the Databricks dataset, that adult data from the UCI Berkeley. We will execute this. To list the files, you can run individual cells here, or you can run the entire notebook at a go. So we will go walk through step by step. So just to check the file is available. So it shows this is the path here of the file on the cluster, and the name of the file, the size. You can also check the contents of the file here, or you can just read it into the Spark and then use Spark to display the contents of the file as well. So here we are reading Spark context.txt file. This is the adult data. Now this is the first part, is just to preview the file. When we actually use the file, we will use the CSV format, which is actually the format of the file. We'll just read that CSV as a text file. And then we take 3 rows from the file and print, just to check the contents of the file. So this is the content of the file. As you can see, these are all the columns which we have mentioned here in the explanation here, review. So age, work, class, education, all of these hours, native country, and the end target label. So all of these data elements are present here: age, education, where is this? This education, marital status, country, and then the label, whether it is less than 50K or greater than 50K. So now we know that the data is, the file is available, the data is available. Now the next part is to load the data, create the data as in our cluster. So from the file, what we do, we create load the file into a table on the Databricks. So before that, if we just drop, if we have created it already in previous sessions, and then we use SQL here to create the table. So we create the table, map all the columns, just like with the file here, using the format. It's the Databricks Spark CSV format. That's the format of the file. And what is the path? Path to the file, and header is false, which means that the file does not have a header here. Once we create this table, go ahead and we'll create the table. Okay, so the table is created in the cluster on the Databricks. Now we can read the data from the table. Spark.table, Spark.table, and the table name. So table name is what we have created here, adult. So we just get the Spark.table adult, and we take columns into the calls. We are not using this variable, but let's display the data set. We will show what is the data we have in the table from what we have loaded from the file. Okay. So this is the data we have in the file. Now we have loaded in the table. So this is the raw table, the raw data in the table format, the beginning, our starting step in the process. Okay. So age, work class, final weight, education, marital status, everything, all of this here, including our income. This is our target label, right? So any questions? Now, okay, no questions. Good. Just check the count. How many rows we have in the table? 32,000. Okay. So now we have done the first part, that is loading the data, first step. Now moving to second step, pre-process the data. That is preparing the data in a way that can be used by the ML algorithm. I mean, ML algorithms cannot just use the raw data as is we have in the tables we have seen. We have text here, a string, we have numbers. We'll have to transform or convert this data, manipulate the data so that we have in a vector format or a numerical format. What I mean by that is, as we see here, we have both numbers and strings, right? So categories, categories and numbers. So what is the categories we had? The categorical data columns or the work class, education, marital status, occupation, relationship, race, sex, and native country. These are all the categorical columns. Now we use the Spark provided functions to convert these into numerical or vector values that can be used by the algorithm. So there are two types we use. One is the string indexer and one-hot encoding, right? So what string indexer does is it just assigns a numerical value for various possible values in a column. Say for example, sex, male, female, right? So it goes ahead and assigns 0 to 1 value, say male, and 1 to female. So all of the values will have a new column mapped to 0 or 1 kind of thing. Same thing for education. So for each of these possible values, list of values, it would assign a numerical value. So that's the string indexer part. On top of that, we use one-hot encoding where it will create a vector, sparse vector from the string indexer. So that it has non-zero values, but it is a multidimensional vector where it can be used in the ML algorithm. So how do we convert these? Is we have a pipeline, Spark pipeline. For now, you just think of a continuous chain of events or transformations that we do. We put it in a pipeline. First, we define our categorical columns. As I have mentioned, we have work class, education, marital status, occupation, all of these where we have string values of a possible list of values. Now we have a stages. So stages is, it's like, as I said in the pipeline, we have a set of events, right? So each event is a stage. So pipeline will contain the number of stages. When you execute, all these stages get executed in a sequential fashion, as and when you add these stages to the array. So what we do, we write all these transformations of converting the categorical columns into numerical or using string indexer, or into a sparse vector using encoder estimator, and then arrange them in a sequence as a stages. And then when you execute that, all the stages get executed in a sequence fashion, in a sequence manner. So for categorical column in these, so for each of this column name, use string indexer. So when you use this string indexer and one-hot encoder estimator, what happens is you give an input column and you also give an output column. So it will not replace the input column, but it will create a new output column which is transformed from the input. For example, we'll see when we execute this first part. But say we have here sex, right, column. Now this is the input for the string indexer, input column name. Output column name, we say sex index. Now we'll have two columns, one is sex and one is sex index. Sex will have the same raw data, and the output column will have the transformed values, 0 or 1 kind of a thing. Okay. So string indexer, input column is category column, that is one of these values. And then output is we are just appending index to the name. So it will be work class index, education index, marital status index, so on and so forth. For each of this column, there will be a corresponding string indexed column. Then we put in the one hot encoder estimator. So the input column for this is a column from string indexer. So we get string indexer dot output column, which means that the column name will be your work class index, education index. So the output of this we take as input to this. And again, we give a name for the output column from the estimator. That is, again, the column name plus class vector. So for each categorical column, we have 3 columns now. So work class, if we take, for example, the raw column will still remain as is, work class. The string indexed column will be work class index. The one hot encoder estimator column will be, output column will be work class vector. Right? Are you clear? There will be 3 columns that are transformed. Any questions on this? I know this is all little bit maybe too much of information to digest, but once we go through and run, it will be very, very simple and very clear.
Can we use something like apply in this setting, or do you have to leave it?
I didn't get that. The voice is not very.
Can we use apply functions for this, or does the Spark?
There are no apply functions. There's a Spark function, string indexer, and one hot encoder estimator. These are
So can we
delivered.
apply on Spark functions, or does it rely on the looping syntax?
As far as we know, I think it relies on these. If you can provide the same output object type, I think we can apply or write your own functions for that implementation, if that's what you mean. Yeah. So once you get this string indexer and encoder, you add it to a stages array. Okay. So for each column, if you look at here, the string indexer is the first stage and the encoder will be the second stage for that column. So when you execute, first this will execute, then this will execute for each of the categorical columns. Okay. Now we have one more thing, actually the output, the final output or the decision label that we want to predict, that is income. So we put income is also a string value. We create a string index for that. Input column is income, output column is label. So we take it as a label and then we create a string indexer. We add that also to the stages. So once these categorical columns run, then the decision column will also run in the stage. Now we take all of these and create a vector assembler. So vector assembler is something like you have 10 categorical columns, right? And numerical columns. So if you take, we have been creating the one hot encoder estimator, which is a sparse vector for each column. Now the vector assembler will create a column, which is a combination of all the columns values into one vector. Okay. So here, if you see, we take column plus class vector. Class vector is actually the output of your one hot encoder estimator. So for each column, we have a class vector, right? So we use that class vector column and the numerical columns as is. We don't do any transformations for numerical columns. So these are all the numerical columns. So we have all the columns here, the transformed class vector columns for categorical values and the numerical columns. We take all of these and create a vector assembler, which is the input is all of these columns and output is called features. Now, when we display this output column, you will know what the features means. And we add this also to the stage. Okay. So let's run this. We are here. Okay, so all the stages are done or put in a array in a sequential manner in the stages. Now we create a pipeline with these stages and execute that stages when you fit the data set into that. And once you fit the data set, you also do the transform data set. That is, your raw data is transformed into all of these numerical columns as a pipeline model. So these are pretty much like boilerplate code you can write. So this holds good for any of the data set. The only thing that varies based on your data set is what are your categorical columns, what are your numerical columns, what is your output column name. So you just have to make changes for those column names as we look at your specific data sets. But overall, most of it is kind of a boilerplate code which would run with any data set with very little minor changes. Okay, so once we check the data set, the actual data set, then we will know what the transformation has been. So these are all the columns, normal columns here. Now, if you look at index, let's check work class education or work class index. Where is this? Yeah. So if you look at the sex index here, it's transformed the values into 0 and 1. That is for male and female. That's what we said when we use the string indexer. That's what it does. But then when you convert into a vector, so this is what it creates a vector of values from each of them. So these are the 3 columns that we spoke about. String indexer will create this output column. One hot encoder will create this column. Now the vector assembler creates this column called feature, where you have values from all of your columns into a sparse vector. Okay. Now, when you actually use your data modeling algorithm, you don't use all of these columns. You just use the transformed columns, the labels. Label, features, and columns. It's more or less the same data set, but we just add the label and features here. So this is the label. So label is, again, as you can see, it is converted as a binary, 0 or 1, which means less than 50K or greater than 50K. So this is the label that has been decided, transformed based on the data. And features is this column where for each of the row, all of the columns values have been converted to a sparse vector for the features. Now finally, what we do once our data set is ready, we just split the data set into 2 parts for step 3 and step 4. One is train the data and test the data. So we split the data set into 70-30, or you can use 80-20, 60-40, whatever is, you feel comfortable, or you can use that 70-30% for the random split and take training data and into test data. These are the 2 data sets. So this will give you the prepared or pre-processed data ready for your data modeling algorithm. Okay. So that is your 32,000 rows have been split into 22,000 and 9,000. This is your training data, and this is your test data for the processing. Then you will go into creating the actual model to run these, the decision tree, random forest, create the model, run the models, and then evaluate your model and make tuning. So all of those steps come in the 3, 4, 5 steps. So here we are ready with the prepared data preparation process to go into the next step. Okay. So any questions still here? Basically, if you look at this, all of these steps, and if you look at this data set, you will easily understand what transformation it has done. It's just like taking the categorical columns and converting it to binary and then into a sparse vector, and then creating a features column with all the input columns. At a very high level, that's what the data preparation we have done. So before that, if your data is not very pure or it has any nulls, you may want to look at how you want to handle your null values, or if you want to drop some of the data. So all of that comes in the first two steps where you want to prepare the data. Okay. So any questions? Or I stop for Srini to take over. So this is the final data set that is ready for the modeling algorithm. Okay, so if we don't have any questions, then I will stop here. Now I can take a 10 minutes break before Srini comes in and I can continue from here.
Okay, yeah, 2-minute break, great.
Yep, thank you guys.
Hi, Blake. How are we doing?
Maybe after cross-pollination.
Hello, Blake.
Yeah, can you hear me?
How are we doing?
We're good. We have one person who's still off, but we could probably keep him. It's been 10 minutes.
Okay, let's do a quick check. Everyone has access to the database cloud and the notebook.
Yeah. Yes.
Okay. Can you please try executing at least one cell? Could you able to start your, you can able to execute?
Yes.
Yes. Okay, very good. So, okay, so any one of you, how was the discussion Harun shared where we are on the data prep? What we did, could someone summarize? I'll do a quick recap, but I want someone to summarize whatever your understanding, or any gaps or any questions you felt. Okay. Before we run the models, I want to quick recap so that I won't take a lot of time on that. But let me share. So I'm here. I hope everyone can see my screen. So let me, yeah. I'm sure you quickly gone through this. Is the data set we want to do for machine learning practice, a binary classification example. So you see Arvind has given this. So you see this is a population data collection. So different data is there, age, working class. So for different people, we know what are their income is less than 50K or more than 50K. So we want to use this data and predict if we get any new data, can we able to predict if the person makes more than 50K or less than 50K. So if I think Harun might have already discussed with you. Rather, let us start executing, everyone. So I'm running this cell. See here. I want everyone to start executing. I don't know if earlier you executed or not. Probably Harun might have given you overview. But so now start executing, everyone. So this is the data already there on the cloud. So it is adult data file. So Harun might have told you it's a very simple. In Spark, you use an object called Spark context, just like Pandas PD. It's already imported on this notebook. So Spark context. So Spark context.txt file, you give the full path of that file, you get a data frame. Not data frame, it is a simple object, raw data. So, and let us see the data. I'm going through few rows in the raw data. I'm taking 3. Take is a one of the method. You're taking 3 and printing it with a for loop. If you see, it is a typical string. It is a file which has a string, different comma separated. It is still a CSV file. There is no data frame. So in Spark, it allows you to load this whole file into a table. So Harun might have told you, you're creating a table adult. So we are enforcing a schema here. So this one is age. Since we already know these are the attributes, using these attributes, you can fairly come up with a schema. So that's what you are creating a table. See here how easily you can create a table here. So it is a Python notebook, but still you can write a SQL here, percentage SQL. So you're creating a table and using a CSV library, and with options. In this path is the file, header is false because it doesn't have any header. If header is true, you can even ignore the header. Those things you can do. You can refer the documentation for your future reference. We don't have to go to every line of the syntax, but I'm running it. So I want everyone to run this. Or a table already exists. So let me drop this table. It's already it exists. It says I'm dropping this table. Everyone, please execute this. If you want to see it, that is also okay. So you got a table here. Now it is there as a table. In fact, some people can, if you want, you can even execute %SQL and just to select %SQL select star from this table. So how the table looks like, want to see. So we are just going through the data. We got the just a data set. So you got it as a table. This is the table. Now let's go. So as we mentioned, we collected the data. We want to prepare the data. When I say prepare the data for machine learning, you all know when you are preparing the data means you are preparing it for classification problem. So a classification problem, many of you know, you talk about label, you talk about features. If you see here, you see this table, I think all of you know there are numerical variables, there are categorical variables. This is numerical variable, marital status is a categorical variables. So if you see in the end, you have income less than 50K or more than 50K. So this is the label, you know. So for this data, we know this data. So how about this? All other columns are features. But if you see, there are numerical and categorical. So in your algorithm, you will have to use, oh, just a minute, my internet is not stable. I got a message. Okay. Please, Blake, remind me if any issue with my voice or anything. Give me a second.
Excuse me. I think we may have already been through this code before. I don't know if you're summarizing or explaining. If you are, what's that?
Cool, thank you. Then I'll go a little bit fast. I'll execute. So to save the time, okay?
Yeah, we have done until the pre-processing steps.
Oh, wonderful. That's great. Thank you, Harun. So let me execute. I executed this. I created this. So I don't need to explain this. So thanks, Harun, and all of you. So let me execute this so that I can. I have a data frame. You just have a count. I'm quickly going through. So Harun might have explained. He's using the pipelines where he is converting into string. Then he is using on-hot encoding. Is moving fast here. Then I'm executing this. This is to convert the label income as a label. Then this is what he's doing. So he is taking separate numerical columns and is assembling with the other vectors. That's good. So Harun might have explained to you already the pipeline concept. The pipeline is to assemble all the steps into stages. So pipeline is also, this concept exists in the scikit-learn also. So where different steps you can do, you can put it into stages and pass that stages into pipeline so that you can apply all those stages onto the data set. So automatically you got the data set. This is all good. So Harun, I think I'm going at a good pace. I'm just skipping.
Yes.
So
we have done until this.
Excellent. So keep relevant column. You don't need all the columns in the world. Basically, you need labels and features. Basically, see, though this table has a lot of other columns, now for your machine learning, you'll be needing this label and features. Okay, now, thank you, Harun. Now everyone, just like it goes just like a scikit, you see the pattern. Now you'll be dividing this into training set and test data. You can use 70, 30 or 80, 20. So I'm just running this. You can able to run and see what are the count. Sorry, excuse me. Okay, so we're going to use two types of models, decision tree and random forest. First, we will use the decision tree classifier. A decision tree goes through the data sets and see the decisions and can able to start splitting it, optimize it, and come to a decision. So in the decision tree, sorry, excuse me. So you will be importing the Spark, PySpark machine learning classification library. You don't have to reinvent. So that library is available. So you are creating an object decision tree classifier. It takes a label, it takes the features, and you can specify some value, 3 or 4. We can able to change later when we are fine-tuning hyperparameters. So you'll start with 3 or 4 or 5. Randomly, you can assign. So with the decision tree object, you are fitting the training data. So I'm running this. So you get that model. You get that model. So let it run. If you have access, I encourage you to run. So this particular, the model is ready. The first 2 steps are done. Preparation of the data is done. You got the data, you prepared the data. Now you create the model. Now this model is through training data. So this model, a decision tree model, can have certain properties like how many number of nodes, how much depth, etc. So let me put it this. Number of nodes it found as 11. Depth is 3 because anyway we give max depth is 3. That's what it comes. So interestingly, you can use for the decision tree model a method called toDebug string that gives you even that your tree in a if then else logic. You know, a decision tree is nothing but if else logic. So that would be created. Of course, it says some numbers like feature 97. We don't intuitively understand that, but basically you can also see the decision tree. You can display the decision tree. Your database notebooks helps. Even a lot of other notebooks also. Jupyter notebooks, I'm not sure in the scikit that that ability is there. It's okay. So then I'm going to use my model, Blake. Now I'm going to run on the test data. So now using the training data, I got the model, and using the transform method, using that model, I'm transforming the test data so that I get my predictions. So if you run that, you see here, you got the predictions. Predictions is a data frame. Please see how nice it is. It is a data frame. Your predictions will come as a table. Again, you have a label, you have feature, but you have all the A's and other things. You see here, it appended raw predictions, probability, and prediction. If you see here, your test data, let me go back. Where is your test data? Your test data, see here, test data and training data, also data frames. You see here, this is the test data. You have label and features, it has up to income. So these are all their attributes. But now after we done the predictions, you got additional columns. You please see. See here, this one, see, raw predictions and predictions. So this is how the same data frame will be started transforming. So if you want to see the what type of, what do you call, types, of course here it displays. You can also use the print schema and display, just for your information. That's good. So once you have these predictions, if you want, you can display selected columns. These are just selected columns. Data frame dot select. What are the labels you want? So that you avoided all other columns. Then next step is once you have the predictions, you should be in a position to evaluate it, how good your model is. So your Spark gives, Blake and team, Spark gives a evaluation binary classification evaluator object. You can use it directly. You don't have to write your custom functions. So there is a PySpark ML evaluation, import binary classification evaluator. You can use that evaluator object using binary classification evaluator. Evaluator.evaluate using your predictions. So your predictions should have basically label and predictions. That's mainly. So basically any evaluation compares your label and predictions. Your label is actual, your predictions are what you predicted through your model. So when I run it, so it does all the heavy lifting, computation, etc. You got your evaluation as 76. Okay. So yeah, please.
How is PySpark.ml.classification different from the library? You have the models in scikit-learn as well, right? Which seems very similar to what you have here. Does the parallel computing happens automatically, or is there like a separate set of codes that you need to put in? And is this better than me using the scikit-learn libraries for doing the same binary classification or random forest?
Oh, that's a very good question. It uses its own libraries because it doesn't call scikit, but it follows the style of scikit because scikit was there for a long time. And a lot of features, even like pipelines concept, is borrowed from scikit. So even one-hot encoding, those are all standard processes. But that's a good question. So it doesn't call any of scikit. These are totally Spark libraries, and the distributed computation happens automatically. You know, that's how your distribution computing happens in stages. It has its own cluster computing mechanism. So all heavy lifting of distributed computing happens. If you have even suppose billion rows of data, it does. It distributes based on the number of cores you have, number of machines you have. The Spark take care of the monitoring. If anything fails, if one machine fails, it again recompute that particular partitions alone. Everything, the data structures. Under the hood, there will be a data structure, a data frame data structure. Quite below, it is even a little bit low level API. It is called RDD, a resilient distributed data set. So they all have all these mechanisms. Does it answer your questions?
Yes, thank you. And then you could, you don't need multiple clusters to run parallel computation. All that is taken care within one cluster.
Yeah, what happens is different. There are different mechanisms in industry. There may be some dedicated clusters where your administrators assign those clusters for your job when you're executing. Now, if you use a cloud computing, like Databricks Cloud, so what happens is every job will have its own cluster. So now here I am running it in a notebook in using UI. That's why I'm using an interactive cluster. But imagine you're running this as a batch. Every night you are running, or every week once you are running. Then what happens is your notebook is scheduled to run, to call a job scheduler, a batch scheduler, and it calls a cluster. It's called job clusters. If I quickly go here, clusters. In clusters, there are interactive clusters and the job clusters. What job clusters that does is, for your job, it spins off a cluster which is pre-configured, or sometimes you can even say auto scale. I want 5-node cluster, but which can scale up to 10 node. So it will start at 5 node, and depending upon if the data is too big, it will go to 6 node, 7 node, 8 node, up to 10 maximum. It goes. It has auto scale features, and it runs the models. It completes that particular notebook or that particular job, and again that particular cluster, the job cluster will die. So that cluster is specific to that job. That's why it is a on-demand dedicated cluster. It just complete the job. It starts. It might take a couple of minutes to start. Then complete the job, maybe 30 minutes or 1 hour. Then the cluster will be will die. Does that help?
Another question is,
Please.
I use Spark on my local machine, so how I use, can I get Spark, install Spark, and then my local machine has a GPU? Do I need to do anything more than like run what we did just now for it to speed up or use GPUs?
Yeah, you can. I don't know in your local machine if you can able to run the GPU, but for CPU definitely you can do. GPUs maybe there may be some option. I haven't run on my local machine on GPU, but you can able to configure, I think, because Spark supports your local machine setup also. But when it is running, it uses processes as a distributed way. It run as if it simulates even your file. You take it as a partitions and try to do. GPU, I'm not sure. Probably we can explore.
Yeah, so if I may, one of the reasons we're installing this on the HPC is there's not much to doing Spark on your local computer because you're already leveraging all of that you run with your normal. But imagine going from your laptop to the HPC, you request a job and you run Spark and it handles all of the distribution itself for you. You don't have to think about it, right? And then you basically get automatic scale up for whatever problem you're running, training or otherwise. And so that's really what we're looking at for trying to understand. I mean, it wouldn't be great to use the word and figure that out. That'd be wonderful. But I mean, like, on the HPC cluster, you can get a hold of hundreds or thousands of CPUs at a time.
So it does the task of distributing multiple jobs or parallel computing without you having to do all of that.
Exactly. Yeah, and it'll actually, what Srini was talking about is it'll actually take your data set, it's smart, and it'll distribute it across all of the, so you could ask for 10 nodes or 50 nodes, and each of them have 28 cores. It'll actually distribute your data set across each of those, do whatever task you're asking it to do, and bring all that back without you having to do all that stuff.
So it is like cluster and cluster has different nodes, and do you give jobs to each of the nodes, or it just automatically distributes jobs to different nodes and then it comes back, and then you can go to the next step?
Yeah, in your case, you'll just tell it to run these steps, and it does all the distribution. You don't have to do any of that.
So yeah, it does make sense to run it on HPC because if I do it on a local machine, I just have one CPU.
Yeah, you're not.
Unless I use my GPU where I can do parallel stuff.
Yeah. And we have GPUs on the HPC, of course. P100s, and on Elgato we have K20s, multiple cores. So we're doing testing now and trying to figure out how to make this very straightforward for people.
Right. Yeah.
So one of my interests here, and I'll give people's names, of course, but one of my interests is how it is you can imagine, like, what kind of research you want to do with this, so that we can make sure that when we're testing it on our side, that we can actually meet those needs. It should be as simple as like y'all logging out of HPC, calling a Spark job, and then just letting it go, running its code.
So we do a lot of image classification, and the data is pretty substantial.
Yeah.
So one other thing we would want to do is like do parallel computing when you're like after you vectorize it. So we don't have access to HPC yet, but so the best alternative is to use GPUs for parallel computing.
Of course. And I mean, I can get you set up. I'm the assistant director of research computing.
Okay, awesome.
I'm in charge of all this stuff.
Okay.
So I'll be happy to set up, all that. But that's the exact use case, basically. Like, we have astronomers who are looking for like exoplanets, and they're doing classification of that, or we have people who are doing like MRI scans and
Gotcha. Yes.
this kind of classification. Oh, wonderful.
Yeah, we do something like we do CT scans, MRIs, and all that.
Awesome. Do you happen to work with non-Koi and all of those folks, or is that a different?
Non-Koi?
Yeah, and
No, we're from Critical Path Institute.
Oh, okay.
Mhm.
Gotcha. Okay, yeah, we should talk. I would be curious to know.
Wonderful, Blake. I think you're getting a lot of momentum. You can able to support the community. Definitely, there's a lot of things going on in the industry. Even we'll be talking Harvard, one of the wonderful software from Uber, they open sourced, where you can do distributed deep learning on multiple GPUs. I think that's what you're aiming for.
Yes.
So one of the great software in the market. Even Amazon uses Harvard. All companies are using Harvard because they spend a lot of time. It in fact borrowed a lot of ideas from HPC, that NPI and some interfaces. Because when you're doing distributed deep learning on GPUs, there will be a lot of I/O. If one machine has issues, because it's a distribution, right? You need to kill everything and rerun. That's how it is historically. But in the HPC community has a lot of algorithms, like all clear and few other algorithms. That's what they used in the industry. So now they are giving back to the community. So I think it's a great collaboration that's going on in the market. So let's continue for time's sake. So I will not run every cell, but I'll just quickly go through. So if you see here, this one evaluator will give you. Now it is a time to hyper tune, hyperparameters you can tune, because even in decision trees, there will be concept called impurity. Either you're using Gini impurity or entropy impurity. You can change it. By default, it is Gini. Then you can change the depth of the trees, 1 to 6, 10, or whatever it is. And you can use the max bins also, different max bins. So for number of different these parameters, if you have to run this whole pipeline again, it will be a lot of tedious. So just like Scikit, Spark also gives a lot of automation in this. It is called parameter grid. It gives you the parameter grid. You can build those parameters and can run those parameter grid. And you are running this parameter grid, you can also do a what you call cross validation, and with number of folds. It means your testing data, training data also will be randomly selected. For one trial, you use one testing data, one training data. For another fold, use one testing data and another training data. So that way it does, and it does the cross validations. And finally, you can take the best models. You can take the, so these APIs will give you the best models. Then you can able to verify and see how good is your improvement is. So that's what I just quickly running this. So you can, if you see what you have before and what is now, you start seeing the improvement. So in the same way, you can do random forest. Random forest, I will not be running it just because I have some other topic to just cover. I know we are running late. So random forest, we can import the random forest. You can create a random forest object. Then again, the same, you can fit for the model. The model will have multiple trees for random forest. So one of the tree you can display. Then you can do the predictions based on that particular thing. We can do the evaluation, because random forest randomly create the decision trees. You know, they're ensemble of decision trees. They're greedy, but they perform better. You know, so you see the improvement almost 89%. Earlier it is 76. So here also you can do what you call parameter grid, because the random forest also will have max depth and max bins. Not only that, you will have number of trees also. This is one extra hyperparameter you have. So you can do the number of folds and cross validation. You can able to do the predictions and finally evaluate. See here, almost you're getting around 90%. So that's a good improvement. So this is a good example, even though it is not a lot of huge data to play with this Spark data frames, etc. So you can do some exploratory analysis here after you got this one. These are simple queries. So bottom line is, you understood now a Spark creates a data frames just like pandas, but everything is distributed. So in industry, there's a huge data and also a lot of distributed computation need to be done, especially on the customer data. Some customers like Apple and some other Samsung or some retails, they have a huge customer base. They need to run models on whole 10 years historical data, their purchases, etc. That will be a good. How does it sound at this moment, Black? Are you good? Let me a few more slides on deep learning, just so we can spend some 20 minutes. Then I'll give some references to Harvard and some notebooks so that you may practice and we can able to further collaborate. Black, what do you think?
Sounds great.
Any questions at this time? Okay. Okay, if not, I will go to this. Okay. 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 Thanks again, guys, staying with me. I know it's afternoon, Pacific time, 4 o'clock. But it's good stuff. Everyone is talking in the industry. Everyone is doing. Everyone knows these are a lot of stuff, especially artificial intelligence, which is deep learning. Machine learning solves some kind of problems when it comes to image classifications. Image classifications are if you want to do a lot of classification in a polynomial sense, in a complex learning relations. When you want to do classification of image detections, and even reading images, all these things needs a what you call next level of learning. You all know that comes into the deep learning aspects. You know, in deep learning, neural networks are the famous. So neural nets and a lot of softwares like TensorFlow, Keras, and a lot of softwares are there. Yeah. But many times in the industry, what happens is when you are applying all these tools, when you are solving a big use case or if you want to productionize an application, there will be a lot of nuts and bolts are involved. A lot of heavy lifting is involved. A lot of software engineering is involved. You know the challenges, Blake. Our community is very enthusiastic to run all this Spark, etc. But when we are serving them, there are a lot of things to make these tools available to them. It's a lot of learning curve for the enterprises also. So that is where so many tools like TensorFlow or PyTorch or scikit-learn, all these tools, when you're working on a distributed environments, and also when the data is flowing, customer data is flowing, again shifting to another softwares and storing images in a clusters and bringing it into TensorFlow. There are a lot of challenges for ordinary enterprises, even though they are big. They're not companies like Facebook. They're not companies like Google. They're just a lot of smart brains work together ahead of the game. Whereas these are enterprises which have been dealing with a lot of structured data, customer data, and serving the customers or serving the operations and as competing each other. So they also want to adopt these technologies. So that's where they rely on this type of technologies like Spark, which interfaces with what you called TensorFlow and PyTorch. So let's quickly touch. I know all of you don't need these basics, but just touch. You all know for images, grayscale images can come in this way, 28 by 28. Color images can come in so they all flattened as inputs. In neural networks, I got a small bit here. My internet is not stable. Just a minute, sorry. The neuron is all about, it takes some inputs, but with some weights. So it is a weighted sum along with some bias. If you are passing it to a function, a activation function, you get an output. So in a simple sense, it takes an input and give an output as a number. Because if this, depending upon your output depends upon your activation function. If the activation function is a sigmoid function, 1 by 1 plus e power minus x, the output will be between 0 and 1. So whatever the inputs you give, whatever the weights you have, your output is always between 0 and 1. So basically this type of mathematical ideas are put into your neural networks. Then if you see your neural networks, where you say deep, you all know, you have input layer. If you pass it to another layer, what happens? So here you have 784 inputs. If you pass it to one particular neuron, you have 784 weights to this. Now you have 16 nodes here. So you have total, each node 784. So it means there are 16 times 785 weights. And each one has its own bias. So there are a lot of parameters. Now imagine you have many more layers. So what happens is these particular weights start increasing. So in industry, sometimes these particular layers, the deep neural layers, could be even 1,000 layer neural networks, or 1,500 layer neural networks. So like that, they all mainly essentially to do a image detection. So what is image detection? You all know. It's basically, you have images, you want to detect the output. You want to classify it as a 1, 0, or 1, or 2, or 10. It's a simple handwritten MNIST data set. Some people think machines are going to really recognize the images. Honestly, it is not recognizing images like human brains. So they use mathematical techniques to identify the images. So mathematical technique means, see here, if you see here, if there is a 7, if this is 8, means the 8, this is the 8 node. So this probability of the 8 is 100. Look here, this is the probability of 5 is 100. Probability of 8 is it is changing. See, this is the one is changing. So if you can make sure this output number is close to 1, 100% means close to 1, close to 1. The output you can change between 0 and 1. So as long as you can manipulate some things so that your output is close to 1. When this is 9, your 9 node should be 1. When it is 5, your 5 node should be 1. So where you have control, when you have inputs are fixed, and the outputs you want to control, the only control we have is weights. So that is what learning is all about. So you have only the control on your weight. So your weights needs to be changed. So you train your neural network on a lot of samples. When you're training it, you will have errors. So there is an algorithm called backpropagation. The backpropagation, it means you start going back, so that you started fixing your weights here, fixing weights here, fixing weights here. If you have even 1,000 node networks, you started fixing slowly from this onwards. So you'll have a learning gradient. So that's how your neural network libraries start learning, and finally you'll come up with some optimized weights. So if you have some neural networks see here in this two what do you call it, this 4 network, but this is input and this is output. These 2 are the deep neural networks, deep layers. You have so many weights and this many bias. So 13,000 knobs you have controls, 13,000 weights or biases. Orally you have control. The learning means finding the right weights. So if you train your neural networks on these particular images, you may be able to come out with a optimized weight, so that your outputs will be accurate. So that's how it is actually. It is not exactly your machine is identifying the image actually. See, in some competitions, ImageNet competitions, there are 148 million parameters. Can you imagine? In a CIFAR 100 ImageNet competition, there are 557 million parameters. As they're learning these parameters, your neural network may be overfit. Overfit means it works very good for training data, But when it is coming to test data or when it is going to unforeseen data, it doesn't do well. It is something like, some of you, maybe some of your friends might go to business schools, spend a lot of money, and if they don't study real world use cases, they'll be more bookish. We call them as a more bookish. When they come to reality, they may not be doing great, but some of your friends may be doing great. They already know the real picture, real world. So that's why you can think them as a war fit to the books. Even in our universities, if people are just focusing on exams and don't have a hands-on coding skills, etc., how difficult, how challenging it is. So nowadays, everything is around supported by data. All research is supported by data. There are a lot of tools we should be able to depend on these data to inferences. So that's why this overfit is also a problem. So that is where there are concepts called dropout, regularization, etc. All these things you don't have to do. Your libraries have those features. You should just know how to use these libraries and Keras and TensorFlow. But in industry nowadays, Spark is another layer on top of this. People are able to build the enterprise AI applications. So coming to neural networks, in the image classifications, convolution neural networks are quite famous. If the images are big, you cannot just scan the whole image. The whole idea of image, as I told you, as you already know, some of you, the machine doesn't recognize the image. In fact, it identifies the patterns. And by the time it comes output, your classification should have a probability of close to 1. That is the whole idea. So in the convolution neural networks, you use some filters, convolution filters. You scan the images not whole at a time. Instead, in a small cells, you repeat it. So that's called convolution operations. You get multiple layers. Then there are certain pooling layers called max pooling to identify the patterns using the max value. If you have 4 values, you take the max out of it. So like that, they do multiple layers, convolution pooling like that. So finally, they will bring the features or patterns as inputs to a regular neural networks. So in a way, output classification can be done. Convolution neural networks are very famous in practice. These are not theoretical. There is some theory behind it, but a lot of practice is done in the industry. That's where Lequan Yu, Yoshia Ben, Eric Hinton, they've done a lot of work on this, and these are very famous. So these particular techniques, convolution neural networks, RNNs, even another is RNN, those are all classified, rather encoded into the libraries, TensorFlow, PyTorch, etc. So Spark, in fact, has the ability to interact with these softwares. So that's in enterprise, people familiar with Spark, they can able to work with the Spark data frames, can able to work with this. Okay. So in this world of deep learning, the Harvard is one of the most famous. I encourage you to start reading it. There is a wonderful paper on top of on it. You can Google it, Harvard. Not Harvard, Harvard, HORORD. So this software is from Uber. It is open sourced. Spark interacts with Harvard very well. So you can distribute your deep learning on the GPUs. Generally, distributing deep learning on GPUs is very difficult. In fact, most of the companies can able to run their projects on single GPU. So even I think, I don't know how many of you has so much data. Some of your projects may fit into one GPU itself. But try to identify some cases, some industry cases where they have so much data where you want to distribute to multiple GPUs. That's where this software comes into the picture. So Harvard, when you're running on Spark, it uses a method. It uses an idea called Harvard Runner. So I have a sample example. I want to share it to you. Give me a second. Sorry for that. Just Give me a second. Okay, this is, I'll quickly go through. Any questions before going here? Blake? It's a little bit fast, but I know some of you might know some of these basics, and I just want to touch that. But I want to encourage a Spark interacts with these particular libraries. See here, Harvard, there is a example, as I mentioned, this is for a distributed deep learning. But before you go for distributed deep learning, you can do for a single node itself. Blake, can you hear me? I can't see the video from your side.
Yeah, so two of the people who had to leave because it's getting late
Okay.
in the image analysis you're doing now. So
can we do we have 4:26? Can we do 4 minutes? Conclude.
Yeah, definitely. I just meant at the end if you'll share the recording with us, so I can get it to those two.
Sure,
So,
absolutely. I'll share the slides and these links also. So Harvard Runner, Keras feminist example. Just basically you prepare your deep learning for a single node using some get data set, then get the model, run the model, train it like that. Then you can migrate it to Harvard. Harvard means when you are using a distributed. So there you just have to import the Harvard libraries, then say Harvard init, then run in similarly as you run before. Then you call it using Harvard Runner. So then you can able to do the distribution. I'll share this link with all of you. Just give me 2 more minutes. Okay. Then next is a lot of people try to do on their own in industry. Just like we have HPC, in industries also will have their own clusters, but managing those clusters is very challenging. So that's why a lot of companies are going for cloud-based big data computation. So Databricks is leading unified computation engine. They innovate, they gave to the community Apache Spark and also now Delta. So they work with community a lot, but at the same time, some companies, a lot of companies want to do that heavy lifting in the Databricks. They choose this. So it has a cloud supported by Azure and AWS, and it uses the Spark runtime, and it is well integrated TensorFlow and PyTorch. And to manage your models, there is another open source software called MLFlow, the whole model model lifecycle management. And now latest is Data Lake, which is meeting a lot of the needs of the companies. And right now you are using Databricks Workspace, just like how I'm running the notebooks. And those notebooks can be productionized. So it is supporting a lot of clients. So some of these clients from Databricks are Cisco, Apple, and a lot of other clients who are leveraging it. Yeah, this is the overall idea I want to give you about Spark and the trends into Delta Lake and how it is interacting in ML, and also how it is end-to-end doing with deep learning. So in a way, it's a complete platform, Spark as an open source. But the enterprises who want to do on the cloud, they are choosing Databricks platforms like this. So you can do all your projects on the HPC, or if your project is funds AWS, because I know in University of Arizona, some projects you can run on AWS or Azure, depending upon what funding you have and what type of agreements you have. Apart from the taking support from HPC, if you have this independent decisions, don't hesitate to explore Databricks Cloud. It's a wonderful, lot of companies are using it. And anyway, I'm great talking to all of you. Blake is a wonderful leader. I always love to associate with him, and looking forward to give more sessions and share what are the little knowledge I know. Any questions?
Flattery will get you everywhere, Srini.
What's that?
The flattery will get you everywhere with me. You know that. Thanks for calling me a leader. I've never heard that one before, but is there any questions or
any questions or comments?
Yeah. No, thank you, Srini. We really appreciate your time. We're all kind of exhausted from doing this all day. So, or I know I am at least. So you can probably too. So thank you very much for hanging in there with us.
Wonderful. I appreciate Harun also joining. I'll share these slides to Blake. If you want to connect with me, you can drop me an email and LinkedIn. And if you are looking for a good position, you can explore. Databricks is a great company. Databricks.com, company's careers. We are hiring. Okay. Kiran, we can't hear you.
Yeah, actually. It was great, actually.
Okay, wonderful. Thank you. Thanks, everyone. Blake, talk to you.
Yeah.
Thanks, everyone.
Thanks, Rin.
Okay, all the best and appreciate for joining me. Thank you.
Talk to you soon, Srini.
Thanks, everyone.